Hello everyone, welcome to the Hands-on Embedded System tutorial. I am going to present a MSP430 Launchpad based 10 watts lamp control microcontroller project using a commercial relay. We shall be focusing on GPIO manipulation and how C language Bitwise operations can be used to effectively isolate the required GPIO by masking technique. An off-the-shelf cheap $5 relay module has been used, which is perfect for this application. It is specified for 5-volt operations but works on 3.3 volts, which is the power supply rail of MSP430G2ET microcontroller. The hardware setup consists of test rig as shown in image, alongside Texas Instrument Code Composer software IDE version 5.2. The Code Composer IDE connects to target Launchpad board EXP430G2 via USB connection. This is the block diagram of the hardware setup. P1.0 GPIO has been used as output pin to control a relay which is powered by a 12 volts, 1 ampere supply. The relay controls the power to the target lamp. P1.3 GPIO is used as an input, which is connected to a push button switch. When button is pressed, P1.3 shorts to ground for the duration of press. This is called user action or user input. Important thing to note here is P1.3 is connected to logic high 3.3 volts via a suitable resistor, a concept known in pull-up. This means that default status of P1.3 is always going to be logic high, as it is pulled up to logic high permanently unless the switch is pressed, which pulls it down to ground or zero level. In this particular case, 0 or logic low on P1.3 would indicate an user action, a concept known as active low input. Conversely, and more commonly, a GPIO pulled down to ground via resistor is called an active high input, as an high logic would indicate an user action. Please note that horizontal bar on P1.3. This notation is generally used for active low or negative logic systems, where logic level low signal means active input. Same applies on output signal. An output signal can also be negative logic. Before we start our hands-on embedded coding session, it is essential that we take a moment to understand some of the crucial software statements and configurations. Understanding these elements will ensure that we are equipped with the knowledge needed to effectively manipulate the hardware. Let's examine the PXDIR register. This is an 8-bit register that plays a pivotal role in controlling the direction of the entire Port X GPIO general purpose input-output. Essentially, this register determines whether each pin within Port X is configured as an input or an output. By setting the appropriate bits within this register, we can dictate how each pin will behave, which is fundamental for proper hardware interaction. Next, we have the PXIN register, which is also an 8-bit register. Its primary function is to read the contents of the entire Port X. It's important to note that this register captures the logic state of all pins within Port X, regardless of their configuration. This means that even if certain pins are set up as outputs, the PXIN register will still provide their current logic states. Moving on, we have PXOut register, another 8-bit register that is crucial for writing data to the entire Port X GPIO. Similar to the PXIN register, the PXOut register can also write data to the pins even if they are configured as inputs. However, it is crucial for the programmer to take responsibility for segregating and masking the GPIO pins they are interested in. Guys, just to clarify that this tutorial is not intended to discuss the installation and configuration of MSP430 Code Composer IDE. If you need help with this, let me know in comments. Let us discuss the actual embedded C code. The first part is variable assignment. SWIN represents the variable that reads the port 1 input GPIO position 0 pin. This is watchdog statement, which we are conveniently going to ignore for now. The next statements are very important as we are going to set up direction for GPIO pins. In this statement, we are telling the compiler that out of 8 pins, 0 to 7, P1.0 is assigned as output. Note how the pin masking has been used. Writing logic 1 at port 1, position 0 GPIO, renders it as output without altering the status of other GPIO. Next statement is telling the compiler that P1.3 is set up as input. Again, note how the pin masking has been used and that this assignment does not affect the previous assignment, which is the key to correct GPIO direction setup. Writing a logic 0 at port 1, position 3, GPIO renders it as input. Any of your new GPIO assignments must not interfere with the previous ones. Next section is the forever for loop. The first statement is the read-off status of P1.3 using the correct GPIO mark. In the F statement block, SWIN is compared to 0x08. If the result of port 1.3 read is high, which is the default status as P1.3, as it is tied to logic high, the push button has not been pressed. If block comparison yields logic true, we set the lamp relay control to off by setting P1.0 logic low or 0. In the else statement, if the result of above comparison is false, the push button has been pressed. P1.0 is set to logic high or 1, and lamp relay control is set to on. Again, notice the way pin masking has been used to alter status of specific I/O pins without affecting others. The last section of software is the mechanical software debouncing solution by inserting a delay before sampling the input again. Let us compile, download, and execute the lamp control program. Hitting the Run button on Code Composer IDE will automatically compile and download the software program to target MSP430 microcontroller dev board via debugger. I am recording the video feed of the actual test rig system and will test the outcome of software download by pressing port 1.3. As you can notice, the lamp is off by default. It is responding to the button press. It turns on while the button is pressed and turns off when button is depressed. Let's see if we can modify the lamp control logic and create a different outcome. As described earlier, P1.3 is active low. It means that when P1.3 is low, lamp relay is switched on, and when it's high, lamp is turned off. As P1.3 is pulled up to high, the default input is high and hence lamp is by default off. How about we try this logic in a different way? What if we reverse the current logic? That means by default lamp would be on, and when P1.3 button is pressed, the lamp is actually turned off. We can achieve it in more than one ways. However, at this time we are going to replace the equal to C operator by not equal to operator and see its effect. Let's make this change and compile and run this logic. As you can notice, when program is downloaded, the default status of lamp is now reversed. It is on now by default. And when button is pressed, it is turned off. The logic has been reversed. In this discussion, we will delve into the GPIO masking statements that we previously used in the software. To begin with, let's focus on how to manipulate the port 1 pin 0 state. If your objective is to set port 1 pin 0 to a high state, the appropriate method to employ is the bitwise logical OR operator. This operator effectively allows you to set port 1 pin 0 on without altering the status of any other general purpose input-output GPIO pins. On the other hand, if you find yourself needing to reset port 1 pin 0, the correct approach involves using the logical bitwise AND operator in conjunction with a negation operator. This combination ensures that port 1 pin 0 is turned off while preserving the states of all other GPIO pins, which remain unaffected by this operation. It's important to highlight that in both scenarios discussed, whether you are setting or resetting, this particular pin is the sole GPIO being manipulated. The rest of the pins remain unchanged, which simplifies the process and minimizes the risk of unintended consequences on other outputs. I hope this explanation has clarified the concept for you. If you still have any lingering questions or need further clarification on any point, please don't hesitate to reach out in the comments. I'm here to help.